to introduce our distinguished speaker, Mike Zoss. He was, well, he got his PhD from Utrecht doing, I don't remember if it was illuminating the QGP, but something with photons.
Illuminating light was the title.
Right. Yeah. And there's actually a YouTube video of him explaining his PhD in 3 minutes. Anyway,
you were on my committee.
Yeah, I was on his committee. Anyway, so yeah, since then, so Mike came here as a postdoc for a couple of years, and then he went to CERN as a CERN fellow, and he now has a distinguished grant for 3 years to put a group together and do physics more with illuminating the QGP. And this paper, I think, is a good foundation for that. So, welcome, Mike.
Thanks. And thanks for inviting me. So as John already hinted, most of what I'll talk about today is a paper that I've worked on for the past, I guess, 2 years or so. So it, also when I was a postdoc here, I always like to do a bit of phenomenology on the side. And this is one of those side projects that became a bit more than just a side project, with basically the big question of how do we measure the temperature of the QGP. So I will give a lot of introduction on what it means to have a temperature and what is a temperature and stuff like this. And I would also really appreciate it because we also got some summer students and everyone. Please interrupt me and ask. So I hope to not lose anyone, and I hope to get many basic questions because they are great. Okay, so please stop me anytime. It's all good. Okay, so the title is Exploring the QGP Temperatures, and we do this traditionally using 2 different probes of the QGP, which are then the thermal photons and the thermal dileptons, and I will cover them. And I'll cover them both of what is sort of the state of the art in the experiment right now, and also from the phenomenology side, which is then carried out by a model that is called Trajectum. Okay, so this is just the simulation code that is called like that. Good. So the evolution of the QGP, just yeah, we have to start somewhere. So let's start here. So before the collision, we have 2 Lorentz contracted pancakes, right? They fly towards each other. They might have some impact parameter. They will hit each other. Then the cross section of the gluons is very large, so the ions will fly through each other. They will create this QGP. So this very hot and dense state of matter that is, yeah, extremely hot. It's like also when I did my grant interview, I tried to convince the committee that it's so hot. It's like 100,000 times hotter than the core of the sun. And I think we all do this physics, but I think it's good to realize that we are studying a droplet of matter that is really unique, right? Within many light years, there's not this thing that we can observe otherwise than in our detectors. Now, this droplet will, of course, it has a tremendous pressure, so it will expand and then cool down. And when it goes back over that phase transition, it will hadronize back into particles. And that's, of course, where we build our detectors and detect all the particles. Now, because this system is extremely hot, and you can just think about it like a black body radiator, it will just start radiating thermal emission. So the quarks and the gluons, so I wrote the few dominant Feynman diagrams on the top. So you have the quark-gluon quantum scattering. So there's a quark in your QGP. It can, for example, absorb a gluon and then emit a photon, right? That's the first diagram that you see there. And then there are the S and the T versions of that, and the swapped one, the U diagram. And this is just a very easy way to create photons because there's just an extra photon created and they escape the medium. And what is special about it is that because the QGP is strongly interacting, the mean free path of a photon, which only interacts electromagnetically, is much larger than the size of the QGP, so it just escapes. So this is completely different than jet physics. Jets traverse, and they have colors, so they will interact with the medium. But once a photon is created, they just escape. This has a cool feature, namely that because the system is very hot early on in the collision, and the production goes with T to the 4, you will create a lot of photons early on. and they will escape. And if you then measure them, you might be sensitive to something that happens very early on in the collision. And this is in contrast to many, many other observables like V2 or whatever that all measure the QGP exactly at freeze out, right? Also, if you do any femtoscopy, anything with a pion, anything with a proton, it's all late stage, let's say. And this can really go back in time. And there are even ways, and I'll show that today, that you can map in time different temperature profiles, for example, or different V2s of the system, how it develops. So there are a few definitions. So indeed, over this whole evolution of the system, we are creating photons. So let's go over that first. First, you collide your lead nuclei. So you have impact of also the protons and the neutrons that are in the lead. So they can create prompt photons, which are very high PT photons. They are not thermal. And later you have the thermal photons, mainly by the high temperature of the QGP. And then further on, you also have fragmentation that come from the jet interacting with the plasma and also not. I mean, you just have your fragmentation photons. And then we always say that the definition of you read about direct photons, those are just, so we define inclusive photons as all the photons that there are, and they are the sum of direct photons plus decay photons, where decay photons are the ones most dominantly coming from pions and eta decays, right? So nearly every particle in a collision is a pion. So you have the plus, minus, and the neutral. So 1/3 of all the particles are neutral pions, and they decay to 2 photons, meaning that almost all photons are coming from pi zeros. And this is also directly the main background to any thermal photon analysis, because you're dominated by like 98% background. Makes it difficult to do the analysis. Okay, are there any questions so far? All good? Nice. Okay, and then so now it's key to try and understand what temperature sort of means and what it is throughout the evolution of this system, right? Okay, so as you might assume, that the temperature is of course a key parameter of the QGP. It's part of the equation of state. So anytime you want to write a model, the temperature is in there, right? Especially if you let it evolve in like a hydrodynamic evolution, etc. And we can obtain it by the shape of the thermal photon emission spectrum. I'll also show that later. And I would like to convince you of something, namely that so far we have a very inconclusive, it's still very inclusive what the temperature of the QGP is. And on the right, there is the famous phase diagram with the potential on the x-axis and the temperature on the y-axis. And the current measurement, and I've written here this dot, the current best measurement of Alice, which happens at mu p = 0, right? And we have the phase transition of lattice QCD is about 150 MeV. And I've written here actually in 2 sigma, the measurement of Alice. So we measure about 350 MeV, plus minus an amount, but we are in no shape or form. We have no measurement that is what we would call a significant observation, be 5 sigma, let's say above what this lattice is predicting. And it's about 2 sigma, okay? This error bar, it's about 2 sigma, maybe 2.5. So we have no conclusive measurement that we are actually creating a system that is above the phase transition temperature predicted by lattice QCD. So it's not just that measuring accurately the temperature is a cool business. I think it would even be very good to establish that we are actually creating a system that is as hot as we claim it to be, right? So currently there's no experimental proof yet that we are creating such a system. It can be a little bit debated whether at RIG or even at earlier measurements at CERN, in what we then call the intermediate mass range of the dileptons, we have a little bit more handle on that. But certainly at the LHC, we have not confirmed the temperature of the QGP. Maybe as a funny side note, if you read the Alice white paper with how we define a QGP, there are 2 criteria, and we have also not measured conclusively any of the criteria that we claim on how a QGP is defined, which is a bit of a It's a funny fact, no? We always say we create QGPs, but we have never measured it in a way conclusively. But this is, I think this would be one step. Now, what I think myself, what is exciting for run 3 is that we have, of course, upgraded the detector. We have now continuous data taking, and we are taking like 50 times the data rate, both in proton-proton and also in lead-lead collisions. So far, it has been quite a struggle to dive into run 3 data, but I think once we unlock it, we will have a tremendous amount of data to analyze. And most of these analyses are very statistics hungry, so that will be very nice.
Mike, before you move us, just because you mentioned the star results in the intermediate mass range, I think I remember that those have an uncertainty of like in the tens of MeV on the temperatures that you extract. So what makes them so much more precise? Is it something about the different UV? Is it something about the dilepton versus photon? Is it?
Yeah, so it's mainly the background.
Yeah.
So it's if you take any particle spectrum like the pions, they are much steeper or flatter at the LHC. So you create many more pions at higher PT, and they keep on feeding down.
Yeah.
So if you have the excess of direct photons, what we call this R gamma, so we have like 2% to 5% direct photons at the LHC, and it's 10 to 20% at RIG.
Yeah.
So you have a 20% signal instead of something that's 5 times smaller. So that makes it much easier.
Aren't they also different measurements? Because isn't the star points temperature at freeze out, and this is temperature of like early?
So there are two. So there are in the. I can come back to your question later if you want.
Yeah.
I can. How it's traditionally measured in that. And then indeed, there's one sort of at freeze out and one in an sort of undefined earlier time. Yeah.
I thought added the difference was also that at the LHC there's a big charm for the dileptons, which is what STAR has done, and that is hard to model.
Yes. Yeah.
Which makes it harder at the LHC because there's basically no charm, so that goes away.
Good.
Yeah, but I think that's certainly true. But I think even if we have the charm under control, I think to measure in the intermediate mass range will still be quite challenging.
Yes, I agree.
Mike?
Yes.
So you would say that at RIC energies, measurement of dileptons is a better way to obtain the QGP temperature than measuring direct photons?
Yeah, so I would be very happy if we could, at the LHC, could do an heavy ion run at injection energy and not ramp up the energy. I think that would be very cool. Which is sort of equivalent. You get to like 250 GeV or so, I think, on injection energy with lead-lead. But you're right. I mean, the signal to background just goes up tremendously if you just lower the beam energy.
So then I guess at RIC, what's the additional motivation to measure photons and instead of dileptons? If
there is no, so I will also show that in the next few slides. There are only more and more arguments to move to dilepton measurements instead of photon measurements. But overall, dileptons are produced a little bit less than the photons. So they are a bit more difficult probe to measure. Photons traditionally are just a little easier. But yeah, I fully agree. So if you would have a very good detector and infinite statistics, everyone should just do dileptons. There's just more information in them. Yeah.
Okay.
It fully overlaps and has more, I think.
That's
but
great.
This might be also the summary slide already of the presentation. So What's another question, maybe? Or oh no, maybe not. Okay. Yeah, so for the people that are maybe not in Alice, and a bit about photon identification. Yeah, so the first point I wanted to make is actually on the left. So in entire run 2, most people here are actually now just starting out, I guess, in Alice in run 3. But in run 2, we had like 1 billion collisions in total, right? And that was all our statistics. That's what we had to do with. And now we have 2023 lead-lead and 2024. And these are just the number of days in November and in October. And the number of collisions here is on the second y-axis. It's not then the luminosity, but the collisions. And one would be here, right? So entire run 1 was this. And you just take it like in a couple of days now in run 3. And this is then in 24 and then in 23. So the amount of data now is just what you can see from these plots is just, yeah, a very large multiplication. So that is just, it's amazing. We have to get all the TPC space charge distortions under control, but I still hope that we're slowly getting there. For the detector, so how do we detect photons? So in this case, photons are a bit interchangeably used between dileptons and photons, and I will also show why. So photons, we measure, of course, in the calorimeters. It's also, I guess, in STAR and other detectors. But for thermal photon analysis, we want to measure as low momentum as possible, right? If possible, we would even like to start at like 10 MeV or so, but this is, well, we start around, let's say 50 to 100 MeV. We can only do that via what we then call the photon conversion method. So the photon is of course stable, but once it traverses the detector, it can interact with some nucleus in some material or some part of the detector, and then it will convert to an electron and a positron pair, okay? So there's first nothing, you measure nothing, and suddenly halfway through your detector, you got an E plus or minus. And in this way, you just have to track 2 electrons. And if your electron tracking is very good, you can reconstruct the secondary vertex and reconstruct your photon, which means that we can use the TPC and something like a TOF to do particle identification, because then, of course, you need to know whether it's an electron or not. So in Alice, for photon detection at this energy, we mainly use the inner detector. So that's the ITS, the TPC, and the TOF. And if we need the electrons, we can select the electron band, right, as function of your momentum. And then it's also obvious that at certain momentums, you get a lot of contaminations from pions and other things. So there's a lot of corrections also being involved. And then at slightly higher momenta, you can sort of activate the time of flight detector and get some additional handle on the electrons. But this is basically it. So what are the measurements so far? So first I'll go a little bit into the experimental side, and then I'll switch a bit more to the phenomenology. So for a few times already, I've said photons and dileptons. What is important is that photons are, of course, real. They are real particles. They're on shell. They have no mass. They're stable. And as I said, if they can convert, so they can interact with some nucleus and then create an E plus E minus pair. And then here on this plot, you can see that you can do sort of a tomography of the secondary vertex of your detector in XY. And you just see here the beam pipe that goes into the screen. This is the first inner layers of your inner tracker, where those conversions happen. And E plus E minus sprout out. And then you just can convert this point. And if you make a histogram of where this happens, you got the tomography of your detector. You basically know how much material is there. And once you then do the whole analysis, you end up with a spectrum like this. And this spectrum is like any black body radiator, you can fit it. And from that fit, you can obtain a temperature. So if it's hotter, you can expect that it will emit more high momentum particles. So it will be more like this. And if it's softer, it will be dying out more quick and emit less high momentum photons. Now, the dileptons, everyone calls them dileptons, but they are really what we are here looking for. They are virtual photons, okay? So they are photons that are not on mass shell, but they have some mass, and they are not stable, and they will always automatically, instantaneously decay into a dilepton pair. That's why we call them dileptons. So within your QGP, it's hot, and it will create photons and virtual photons. And those virtual photons will just immediately go into E plus and minus. It then does not need any material to convert, right? There is no flight time or anything like that. But it does mean that their identification nearly completely overlaps because you're just searching for 2 electron tracks. But they all happen at the primary vertex. So many of the analysis things overlap. What then the nice thing is that you can perform the measurements not just as function of the momentum of your photon, but you can also do it as function of invariant mass. Okay, if you would plot this for photons, you just get a bin at 0, right? Because photons have 0 mass. But the dileptons have an invariant mass. And then if you measure that, you basically get what they call the spectral function of QCD, right? And then you get the whole zoo of resonances, everything. you get these. This is the J psi, for example, going to E plus E minus, and there's the rho and the omega. And then there's here, it tends to go to infinite because you tend to go to the real limit where you get just your pi zeros that will go again to photons. So that is what you measure. And then from this, what you do in this, so if you do this whole analysis, you have to make, so this is your whole spectral function with everything that feeds into electrons. So it can also be even a BB bar that annihilate to E plus E minus, right? There's a lot of components that go in, and there you invoke, or you need to construct what they call a cocktail with all known sources of electrons. And then you have to approximate real life as good as you can. So this will come with uncertainties. And then what you hope to do is to find an excess on top of this cocktail. And this might then be radiation from the QGP. And this radiation of the QGP can be present everywhere, but of course it will die out a little bit towards very high invariant masses. And then also as function of time, the evolution of your plasma, you can also already imagine that if the system is very hot, the probability to create a virtual photon that is more off shell or has higher invariant mass is a little bit higher than when the system is very cool. So if you would do a measurement of dileptons as function of this invariant mass, you can basically go through the different times of your evolution of the QGP. Okay, and then what they call a measurement, so go back to your question, Andrew, if some measurement of the QGP, so they don't measure right inside these resonance peaks, but if you measure in this region, they call it the intermediate mass region. But this is higher invariant mass, so this is when the system was very hot. And there you get a temperature that might be related to very early on during your QGP. And if all Alice measurements at least, and then also the ones at Rick, they also do something at the low invariant mass, and then you get your temperature at freeze out because it goes towards zero, and then you approximate the real photon. Again, okay.
So I'm a little bit confused between the dilepton and the photon. If the dilepton also turns into E plus and E minus, you said it was instantaneous. How are you able to tell the difference between that and a photon when it comes off? And also, how are you able to know that a dilepton was even there if it immediately turns into E plus E minus?
So the dilepton rates are really still much, much smaller than the photons. So if you just measure them, you would, so the real photons also end up in this one. Additionally, for the photon, there's also something like you have more handle on the PID, that it's a real photon. You have also the Armenteros-Podolansky plot, if you know about this. Yeah, there's like two axes that if you then plot the energy asymmetry versus the QT, I think, which is the transverse energy of your pair, then you get particles that, neutral particles that decay, they form a certain band. So you get a lambda band and you get a photon band. And then in this way, you can also have an additional handle on that it's actually a photon. Yeah. But I mean, if it has any invariant mass, like here, it will automatically also be a dilepton. So in a way, if you do this analysis, you also automatically filter out photons. So it goes a bit both ways. Yeah. So then to quickly go over the analysis, which is a bit similar than for both, I already went over it quite a bit. So the first step of any of these analyses is that you have to identify your photons and dileptons. There's a very big effort to really understand all the backgrounds and the detector inefficiencies. If you did any analysis yourself, you know how difficult this can be. Then once you've done that, you obtain your spectra, which is for dileptons something like this versus invariant mass, or for photons versus PT. And you can calculate the contribution for your thermal emissions. And then you can extract the QGP temperature. And I'll also go a bit more into that, how that works. So now for real photons, so direct photon spectra, you have the main result here on the right, which is a reanalysis of the run 1 data. So this is a 2.76 TeV. And it uses this new corrected material budget, where we more precisely know the material budget of the detector and can reduce the uncertainties. And how we do then obtain the direct photons spectrum is via a measurement of this direct photon excess. And we know the number of inclusive photons, so all the photons, and then there's a bit of a mathematical trick, and you get this spectra. Now, if you fit this, so this is again basically the Y formula there. You can reshape it to this form, just the 3 differential of the number of photons per momentum, and this is proportional to this black body radiator term, and you can fit it with just an exponential, so e to the power minus e, so that just goes along the x-axis, and there's this 1 over t. Okay, this 1 over t is then just the slope of your spectrum. Now here you can fit this on the right, so you have your direct photon spectrum as function of pt for 2 different centrality bins. So in red is the fully central collisions, and in green is the slightly offset, 20 to 40%, so semi-central collisions. You can fit both of them, and what we then obtain is written here. So it's both around 340 plus minus quite some huge uncertainty. Okay, and this is basically this red point that I had also on the phase diagram. And you also, what you notice is that the temperature is not really different, whether you have a central head-on collision or semi-central. Now, what is sort of the thing that withholds us from doing a good temperature measurement with real photons is the fact that your plasma is expanding, and it expands with about 0.3 C, so like 30% of the speed of light. So you get a real blue shift, because the surface is emitting these photons, and it's like, yeah, the police car is coming at you, right? You get this blue shift, and the energy gets shifted higher, and this is completely giving a shift to your spectrum. So if you measure a temperature, it was not really the temperature. And then it becomes very model dependent to unfold that. So if you would then measure it, it's not really a model independent way to say what the temperature of QGP is. So real photons are unfortunately affected by blue shift, and this is creating a difficulty. Okay, so now I went on this quest to do more phenomenology and then understand better what the temperature of the QGP is. Okay, and back when I was a postdoc, I also invited Govert at some point for an NPA seminar. And Govert is also, like me, he did his PhD in Utrecht, and he did a huge gamble in his PhD. Namely, he thought to rewrite the entire, write from scratch, a new framework to do heavy ion collision simulations, right? He thought, okay, let's do complete Trento, let's rewrite music, let's rewrite the whole code with the afterburners and everything. That actually worked, and now it's one of the best models, I think. I'm very biased because he's also a friend, but it's one of the best models, I think, on the market to do, like, on one end, the Bayesian analysis to get all the parameters of the QGP, but also things like this. Now, what I asked him to do is to create an additional output file about temperatures, and then we also wrote code to include thermal emissions, so both for real photons and for dileptons. And now in this model, which basically then consists of an initial state, and then you can switch between Glaube or Trento and all these things. There's a pre-equilibrium, there's your hydrodynamics, and then with SMASH or UQMB, you can do your hadronic afterburner. It's what's sort of under the hood. And then it is now in this hydrodynamic phase, it's also creating these thermal photons, okay, and thermal dileptons. And just to try to imagine what sort of temperatures you could define. So of course, and that's a bit written here. So you could define a temperature at time equals 0. This is just whenever your ions overlap and you create your initial state, you can have a temperature at time equals 0, and it could be space dependent, right? Anywhere within this first thing. And this is governed by the physics of the initial state, and this is also what you put into your hydrodynamics. Then you can do, of course, a temperature, because I don't know if everyone knows this. If you do a hydrodynamic simulation, it's sort of a finite element method, right? So you have fluid cells, and those fluid cells all talk to each other via this, just the equations of your hydrodynamics. And these cells have a specific size and property, right? And that's how they talk to one another. And basically what you can ask the hydro, what is the entropy there? And what is this quantity? What is this quantity there, right? You can ask this for any cell. So as function of time and space, you can have a local temperature of your plasma all throughout its evolution. You can, if you want, you can write it all to a file for every collision. This would be a bit much. What you can also do is you can have an average temperature as function of time. So you can have an average temperature of your whole plasma at time equals 0 or halfway through your QGP or at the end. Or you can do a fully averaged temperature that you just you average space and you also average the whole evolution and you get one temperature. And then of course you have this effective temperature, and this is the only one that we can access experimentally by doing like a photon measurement or a dilepton measurement, right? So somehow this is our model, and this is how we want to cross-check things. So the only way to do it, so you have the model, you can already access all the temperatures, and it's constrained by Bayesian analysis, so the evolution works quite well. Now, after implementing photons, you can do the measurement in the model as if it is experiment, and then you can extract an effective temperature and then connect it to these other temperature quantities. And that is exactly what we're doing. And
it's a fine detail, but like, is it really at t equals 0?
Yeah,
Because
that's
it
a
should
fine
be at
detail.
some 0.6 or something, right?
Yeah,
There's
so
some
there-
pre-equilibrium in Trajectum. Yeah.
there is a it's not a t, but then it's a tau, and tau is even one of the Bayesian, the parameters that go into the Bayesian fit. So indeed, you have your initial state, then you have a moment that you start in hydro. Then what this model does, it's 3 streams. It has to connect your initial state to the start of your hydro. And the time you let this sort of evolve is a parameter even.
Mm-hmm.
Yeah, so you can set it to some value, but usually it's around 0.8 Fermi over C. That would be then called the time 0 of your hydro, but it's already evolving your initial state for a while.
Okay, good. Yeah.
Yeah, it might be like, I don't know, 10% or so of your entire lifetime of the QGP. Yeah.
So this initial time before hydro and the temperature that you input into hydro, they're both Bayesian parameters?
Yes.
Okay. You don't just.
Yes, but also indirectly. So most, or if you use Trento as an initial state model, Trento comes with a few parameters. And depending on what those parameters are, your initial entropy density will change. And depending on how big even you would choose your cell size, or you average over space, fine. If you change your parameters of your Trento, the temperatures will change. Yeah. Yeah. And then it's also a highly dependent statement how coarse-grained you take your Trento, because it can be also IP plasma, for example. If you know the pictures, they are very spiky in entropy density compared to some other ones. And those can have very, very high local temperatures, even like almost a G, something crazy. But if you let that evolve for some time tau, then you basically wash out most extreme temperatures and you get something more average. And then already, I'll also show it, I guess, here. We can make it more concrete. So what is now in these plots is just the temperature of your QGP in a model that is constrained well by all the experimental data that we have, right? And we have on the left the temperature as function of centrality, and on the right it's the average temperature over space as function of time in the collision. Okay, so maybe it's easier to start on the right. And there are different centralities here. So we can just follow for a moment the red one, which is fully central collisions. You see that they roughly start out, and that's why this is gray. That's Helen, your question, because this is basically when it starts to be colored, it's when the hydro is really activated. And before that, it's a little bit extrapolated to show you where it somewhat goes. Okay. But a fully central collisions is about 400 MeV in the beginning. And you already see that after 1 Fermi over C or 2 Fermi over C, it rapidly drops. And after 10 Fermi over C, that's about the lifetime of a QGP droplet in central collisions, okay? If you go more peripheral, it will get colder. And if you go more and more peripheral, it even gets colder. And so it's about 260, 270, 200, almost 300 MeV for the peripheral ones. And they live shorter. That's also understood because if you offset it, your droplet will be smaller, so it also dies out. Now on the left, it's as function of centrality. And here are basically, if I go back one step, you have these different quantities that you could define of the temperature. And that is what is here. So the red band is the maximum temperature you will find in your plasma at the moment you start your hydrogenization, hydrodynamics. So that is this tau. So basically, you can think of it as tau zero when you start your hydrodynamics, right? Or time is zero. And that is, of course, the hottest temperature. There might be a hotspot that it's even like 800 MeV in your plasma, right? And this band is basically your error bar of the distribution or the width of this distribution. Yeah, and then you can also average, you take your plasma at initialization time of your plasma, but you average over the space, right? So you average out your hotspots. Then you get orange band. And you can also average over time, so your whole evolution of the plasma. And then you get this blue band. It's much more precise because it also makes sense. There's one big difference now, sort of, is that there's not such a huge centrality dependence anymore if you just integrate completely over time. And then you wash out these sort of things, right? I mean, at time equals 0, central collisions are much hotter than peripheral collisions, but if you average over the whole evolution, this gets a little bit washed out. And this is because the plasma, for a long time at a later stage, just spends more time in being cooler, right? And that's a little bit how this average works. I remember when I was a postdoc here, we had, me and Alan, we were thinking like, are central collisions even hotter than peripheral or something, right? That's a little bit how this whole story started. So now it's like sort of in the full form, we have more information on this. So that's quite cool. But this is just in the model. It doesn't yet invoke any dileptons or any photons or anything.
But I guess I don't know, how do you map from left to right? Because like you said, the central on the right says the temperature, the mean temperature at 0.6 is of order 400. So how is the mean temperature now above 500 on the left? Shouldn't these two numbers be the same? What am I reading wrong?
So the red band here,
It's just the hottest hot.
is the hottest. Yeah, exactly. So one way is to compare this orange one,
Yeah.
which at least at time equals 0. That should map a bit to this line.
It sort of doesn't, yeah? Because that's sitting at 400 for the red, which is the most central. So I should sit at that end, which is above 5.
Yeah, that's true. I would have to think about that, actually.
And they just different parameters.
Yeah, we do. Yeah, that cannot be the full answer. So we do run with different parameter sets, but yeah, I would have to look into that. It's a good point. Yeah.
And then your mean, the blue, like, is this because you go to such a long T? Because they look pretty linear. So I'm surprised at those averages.
Yeah, so this is a linear because it's in log scale also to see with this Birken scaling how it goes. Because it is expected to cool off with this
Okay.
-1/3 to the power 1.
I'm not sure how to read that box.
So it's a bit difficult to really, if you would plot this in a linear scale, then it's more obvious to see what the sort of the average then.
I missed that it was some loggy.
Yeah, so it's a bit of a funny log scale. Yeah. Yeah. Yeah, but to your first, I'll get in. I'll check. Yeah. Okay, so now we go to the point where we have implemented all the thermal emissions. So we have the photons, for example, on the left and the dileptons on the right. So there's a whole theoretical rate equation and some data points that constrain this to then allow you to put this in such a model. And then you, of course, can have more output files and make sure that you can document correctly your thermal photons and your thermal dileptons. And here you see the PT spectra for both as function of the collision centrality. And this we of course also compare to experimental data, and we're quite in a good ballpark. So that's nice. So we also confirm all the papers by like Charles Gale and François Paquet and stuff like this. What I also think is nice is that most of the papers that are about thermal photon emission use some form of music with one set of parameters. And this is the first time that we have sort of a model that is fully constrained by Bayesian analysis that is also used for many other observables. It also very accurately reproduce V2, V3 up until whatever, and also particle production spectra, that this model also does this. So it's not just, because you have many models on the market that is, for example, able to describe your V2, but it doesn't really do well on pion production, but this one now does all of it and also does this. I think that's quite nice. So we had the PT spectra. Now for the dileptons, you also have your invariant mass spectra. Now, I didn't show this yet, so that's why I show it here. If you want to extract your effective temperature from dileptons, you can do that with this formula. So if I go back just 1 second, for the real photons, it was the simple exponential. And now it's still simple. It still has this exponential, but there's a prefactor. And it's still related to the slope of your invariant mass spectrum. Yes.
So when you say photons, do you just mean that the virtual photon contribution from dileptons have been subtracted or just not included in the simulation?
Yeah, they are not included, just via the selection of either dileptons or the photons. Yeah.
Okay. But then I guess the measurement that you showed from Elise, that's also done, like this removal of
Yes.
dileptons. Okay.
Yeah, so if you do a real photon analysis, you don't have to. So because you have a conversion point of your photons in the material somewhere, you already require that this conversion point is not at the primary vertex. This makes it auto reject all dileptons, right? If you say it has, by minimum, it has to convert in the first layer of the ITS, and you have a conversion point there. So you have first nothing and then E plus E minus, it was already not a dilepton. Because a dilepton instantaneously decays in E plus E minus, so it will be indistinguishable from the primary vertex.
So if you measure these photons through calorimeters, can you also reconstruct where they convert to dileptons in the calorimeter?
So if you measure a photon as a photon that hits a calorimeter, it's by definition not a converted photon.
Mm-hmm. I assume like Phoenix did their measurement through calorimeter.
Yes, and then they will measure real photons that do not convert. And they will always assume in any calorimeter, if you have a cluster, you will always assume the origin is the primary vertex because there's no additional tracking in between.
So then they would need to subtract dileptons from their calorimeter measurement.
No, but they will never enter the analysis because then you would have to do tracking on the electron tracks. Right? And it's an additional problem that electron tracks are like photons creating photon-like signal in calorimeters, but this is a very subdominant effect. Yeah. And calorimeters usually operate above 1 GeV or so, and this is where these rates are already quite low. Yeah.
On the right, it looks like the 0.2 to 1 PT line has a much steeper slope than the other ones. Do we know why?
Yes. Yeah. Yeah, that's very interesting because so this has to do with, I'll also come to that in the next slides. If you go throughout the evolution of the QGP, in the beginning it's very hot. So you will have some sort of PT spectra that is very specific to very hot QGP. And there's also another PT spectra that is sort of related to later times. So now you can also invert that if you would have a different PT range for your photon. So you could say, this is a higher PT than this. Mm-hmm. So because this is higher PT, you would require on average a higher temperature.
Yeah.
So this already shows in a way, so the reason why this is that different PT cuts will imply different average emission times of the dileptons. And this changes the shape. So this already shows that if you make indeed analysis selection cuts, you will highlight different points of the evolution of the QGP. Yeah, and that's why the shape changes. Okay. What?
I'm gonna meet with you later on.
Yeah,
It's more
perfect,
later.
So here we did a bit of a yeah, it's both a mental exercise and to see if everything that we know makes sense. So what we did is we fixed. So we have our QGP evolution, and what we said in the model is that we choose a fixed temperature, let's say 300 MeV, and whenever the evolution goes on and there is a cell that is that fixed temperature, so let's say 300 MeV, then we will allow it to emit photons, okay? So we don't fix the entire temperature of the QGP, but we choose a specific temperature and we only let it emit if it's that certain temperature. So the whole evolution will just happen, and whenever any cell is exactly the temperature, plus minus 1 MeV or so, we allow it to emit, okay? What is nice about that is that we can ask to fix, for example, the fluid temperature at 300 MeV. We let everything evolve. We get a spectrum from that, right? Then we do our photon and the dilepton analysis, and we check what if we fit this spectrum, do we get back that temperature? It's a very logical question, right? So if we allow or we fix the temperature, exactly, and then we fit it, we want to find back the same answer. So here in the dotted line, this is the y equals x, okay? And this is the one we find in the model experiment. So we do like as if it's experiment, and this is the fixing of this temperature. So first we run it once, and we fix it on this temperature. Then we run it again, we fix it at that temperature. We run it again, and we only allow it to emit at this, and then we go on, okay? So this dotted line is 300, 300, and 400, 400, okay? That's y equals x. Now there are 4 different lines in here. There's the dilepton one and 3 photon ones. So what do we then see? What is something you see now?
That dilepton one looks pretty good.
It's on top, right? Yeah. So the dilepton measurement, if we fit using that formula I showed earlier, if you fit your spectrum that comes out, so you just let it allow to emit your temperature, you get your spectra like here. So this is this fixing, right? You fix your at 175, at 250, at 450, you'll get different invariant mass spectra. You fit it, you get your temperature. So if we fix it at 200, the dilepton fit gives us back 200. If you fix it at 300, you get back 300, 400, 400. So this is great, and this is also, yeah.
So I understand that there's a bunch of like backgrounds for measuring photons, and so it's a hard measurement, but if you're doing it presumably correctly, what makes it give you the wrong-ish answer for like the low momentum?
Yeah, exactly. Yeah, that is exactly what I'll come to.
Okay.
Then he said his weak point.
Yeah, exactly. Yeah. Yeah, so the good thing about dileptons is that they do not get this blue shift like photons do, because dileptons you measure as function of invariant mass, and invariant mass is invariant, which means that this emission that goes with 0.3 C, this boost, if you measure it, it does not care about your frame of reference, so you don't get this blue shift. So that is nice about the dileptons. And then it's also shown that dileptons are in fact on this y equals x. And for us, this is double nice. You confirm that it's the case. In the model, we also hope that this is the case. It also shows that the fit formula that is sort of in this in the literature was also good. Now, if you go to photons, they at very high temperatures, it's sort of the case. But at lower temperatures, which is very late during the emission, that's where a lot of this blue shift sort of happens, right? And the spectra gets blue shifted, meaning more energy, right? And that is why this line tends to depart from this y equals x, and why all the measurements, because most will return about 300 MeV. And now you can, if you, this is I wouldn't advise it, but you can do it like a literal study. You try to find all the Rick papers, Phoenix, Star, all the Alice papers, whatever, NA61. Just look at any temperature measurement ever done. It's always 300 MeV for photons, okay? And it doesn't matter beam energy, doesn't matter centrality, nothing really matters. It always returns 300, plus minus a huge error bar. And this is the reason, right? Just they get blue shifted, and they all get blue shifted towards this value roughly. So that's why it's not y equals x for photons. It's a blue shift. Yeah.
It's a good go.
So yeah, my question was going to be, you've mentioned that the blue shift correction is very model dependent, but given that you are making the model here, if you did do the correction, would it just be y equals x?
Yeah, but because it's a correction that it's hard to just write down an effective correction for something like this, because it's a quantity that evolves over time. And then I don't think it's ever been done to try and just sort of unfold one spectrum to
You
get
could,
your
yeah,
right
couldn't
temperature.
you? Because you're fixing it at emitting at a temperature, I guess it must have a blue shift.
Yeah, so you in the model you could do it per temperature probably.
Right, I mean, you wouldn't be something you could do it experimentally, but I guess
Yeah,
to confirm Andrew's question.
yeah. So yeah, in the model you could. Yeah, because sort of the inverse of this would be already the correction, sort of the departure from the y equals x. So,
So you're comparing the photons and dileptons here, and the claim is that because of the blue shift effect, if you go to lower temperatures for the photons, you have this the blue shift effect is largest there. But so then wouldn't we want to compare to the dileptons at low invariant mass, because that's the later stage, and we would show, oh, that actually there really is nothing happening there. Did you also look at below 1 GeV for the dileptons? Below 1 GeV invariant mass for the.
no, because here we always stay in this. So for this fit to hold, you already see it a little bit that it's not so linear if you go to very low invariant mass.
Okay.
And this is also where the rate equations to put it into the model, they break down at some point. Okay. So they're always only trustworthy above a certain value.
Okay, I see.
Wouldn't that be the low mass range where it would be sensitive to the freeze-out temperature instead of the initial one?
Yeah. The lower you go in invariant mass, the later you go. Yeah.
That's what you see.
Oh, you mean like going to the left side of the plot?
I just meant
For this discussion, this plot is a little misleading because we are sort of fixing this temperature that allows it to emit at a certain time, but it's not really biasing towards any time. Right? It is still true that low fluid temperatures happen more late time, but it's not like plots like here. It's a little bit different.
Okay, so here if you have low mass range dileptons, they're also sort of created in the QGP phase instead of the later time where the measurements claim to be related to the freeze out.
I think there might be some confusion on terms. And maybe another thing. So in the model, we only create dileptons and photons in the QGP phase, okay? Because otherwise, before the QGP phase, you have your Trento or your pre-equilibrium, and we don't create any photons there. In reality, there are probably photons created, or quite sure there are photons created. And post-hydro, we do have photon creation because you have your scatterings of your various particles that create photons from the hadron gas, so they are included. When we say we are measuring closer to freeze out, this can still mean like towards the end of your hydro. Becomes a bit equivalent to measuring your freeze out, right? So late times in your hydro evolution would be close to freeze out. So how freeze out is handled, so maybe this helps. So you, in a hydro model, you let everything evolve with all your finite elements, right? You put in your model a switching temperature, that if a cell hits a certain temperature, and in Trajectum it's like 150 MeV, then it's staged to do nothing anymore, okay? And then you let your plasma evolve, and when every cell hits this switching temperature of 150 MeV, then it's static. And then you hand it over to the next algorithm, which will hadronize it. This is usually done with this Cooper-Frye framework. We'll just statistically sample the surface and create particles until all the energy is attributed to some particle. This is hadronization. And this exact time is what we call freeze out, right? This is also the surface that most femtoscopy measurements would measure.
But I guess I was thinking, maybe this is misunderstanding that I have, that the photons created from the hadron gas is not really probing the temperature of the QGP. Correct. And that one is closer to the temperature of the freeze out. Is that correct?
So the hadron gas by definition is after your QGP phase, let's say. And it's also true that there's probably a very dominant contribution of photons from the hadron gas. So not dileptons, but photons, okay? It could be that even the majority of thermal photons are created by the hadron gas. So we have a bunch created during the QGP phase and a bunch of the hadron gas. So if you would do experimentally a measurement, you're probably dominated by a temperature that is even lower than the one at freeze out. The freeze out is in the middle between those two states.
Freeze out is in the middle between QGP and hadron gas.
Yeah, that is what is the definition of the freeze out. It's like you freeze your QGP and then you hadronize. Right? It's basically this. I think in reality it's slightly more complicated, right? Because if you have a peripheral collision and you look at the periphery of your peripheral collision, it probably doesn't even reach temperatures to form a QGP, right? So that is already a hadron gas. So even early times you could have hadron gas, right? There could also things like hotspots, they generate V2. So you know there's some asymmetry in your system. So there could be regions that are much lower temperature, right? So freeze out is not really that you go from 0 to freeze out and everything, but that's how the model does it. But basically freeze out is really this time the QGP stops to exist and you instantaneously make everything a particle. That's freeze out.
So then low mass range dileptons or photons are sensitive to the freeze out temperature. So then
They're sensitive in the sense that the majority of them are produced very close to that time that you would call freeze out. Yeah.
So I guess I was thinking that would be why you didn't include the low mass ones, because you are trying to look at the temperature of the QGP instead of the hadron gas.
Yeah, but where he's frozen is that they're only emitting at a temperature. So normally you're measuring, I think where some of the confusion Mike is coming in is like, experimentally, we would measure an integral of all the temperatures, right? And then the low mass region is dominated by the hadronic one. But what Mike was showing was the low mass at a temperature that's very hot. And that's where it becomes shouldn't look there point.
Yeah, exactly. Right? Yeah. But you can also imagine if you have one cell with a rate equation at a certain temperature, this will still emit a whole spectrum. It is not that if a temperature is 500 MeV, it will not always emit only photons at 200 MeV, right? This is still gonna be like a black body, like literally it will be a black body spectrum on its own. So the whole evolution is like it's like a convolution of all these black body spectrums of all your cells in your QGP, right?
Okay.
Yeah?
Yeah.
So yeah, but that's a good point what Helen said. Even a high temperature will emit low invariant mass photons. So I'm only 2 slides away from the final. There will be also a very nice money plot that I think will be on the next slide. So here we have the 2 effective temperatures as if you would use the model as an experiment and you would measure the temperature as function of your collision centrality. And then on the left, we have photons for different PT cuts. And on the right, you have the dileptons for different invariant mass cuts. And as you then can, and then in blue, it's each time the average temperature from the model. Okay? And here it's indeed also the switching temperature when you would want to go to freeze out, and this is indeed 150 MeV. This line. So here you see that for different PT bins of your effective temperature, you can see that lower invariant mass in general gets emitted later, so the average temperature is lower than if you would go to very high PT for thermal photons. Okay, this is qualitatively the same what you would see for the dileptons, where if you go from low invariant mass to higher invariant mass, the higher invariant mass are emitted earlier, so they give hotter temperatures. Okay. What you also see is that most of these measurements for any PT region for the photons are in this ballpark of 300 MeV. That is also the case there, but we also learned from the other study that the left is affected by blue shift and the right is not. So if you would measure the right side, then you know that the plasma was actually also the temperature. Okay. And this is something that we can then expect in experiment if you would do a centrality dependent study of the temperature.
I have a question. So on the left, the 2 to 4 range is above 300, which is where on the last slide that started agreeing with the dileptons. So like, does that correspond exactly to the one that's also kind of the same-ish color on the right? Like, are they measuring the exact same time? Because they seem to agree.
Yeah, that is just almost a coincidence, because comparing a PT bin of photons to a invariant mass bin of your dileptons is not equivalent. Yeah, of course they are correlated a bit. Like if you have the energy of an it's the P squared plus M squared, but yeah. Yeah, so a little bit, but not completely. No. Okay, so then the key message here is, I can just read it out loud because I think it's a sort of a strong point. So while the resulting effective temperature for photons and dileptons are similar, the photons are unreliable, period, because they are blue shifted. They are not a model independent way of measuring temperature. And they would never give you a proof that your temperature is above this pseudo-critical temperature that would form the QGP, or what is then motivated by lattice QCD. But dileptons can, but depending on any analysis cut, it will always be biased to some time during your evolution. Okay, so it is still not the case that you can really measure a temperature that is really the temperature of the QGP as a whole, but it will always be biased to some time.
But it's not completely true that whatever you measure for as an effective temperature, that you could never prove it, right? If you go back to the slide before, if you measure something like effective temperature of, I don't know, 450, then you would know that it would also be a actual temperature of 150, right?
Yeah, so at very high temperatures, they do become equivalent and the blue shift becomes less. That's true.
But for what we measure at the moment, that's true.
Yeah, that's a good point. So if it's very high, then it's also true that indeed. So maybe this should be with some grains of salt. If you measure a couple hundreds of MeV, we still know that we are creating a system that is at least very hot. Because if it was a system that is, I don't know, room temperature, you would never get something like that, right? There's no blue shift that can just push it to 300 MeV or something. So, and then via the model, you could also expect or extract a little bit what the temperature ballpark should be, because you can also model the blue shift. But indeed, my key message is that indeed the dileptons are directly a very powerful tool to measure it.
Moving on to that, Mike, before you get to your money plot. So, like, do we have a limit on what the blue shift can be? Because if that other plot, if my blue shift, like, how sensitive is it? Like, if I just made the blue shift a tiny bit more, would I just pull away at 400? I guess I haven't got a good feel for sort of what that does. If I say it's 0.3 and 0.31, am I pulling that away from the x equals y line dramatically more?
Yeah, that's a good point. Yeah, one could even play in a model to somehow, I don't know how that would work, that you would increase this velocity somehow, but that has to do, yeah, no, that's directly your hydro equations. Because it's the pressure that, I was wondering if you could change the velocity of your field. You can play with the blue shift and get an upper limit on how much it could do. But I think here you can see it pretty much, because most of the system actually spends a large time at lower temperatures, right? Because it expands and the volume factor. So I think at most it can be this, but that's a lot. Right? This is basically your switching temperature, what you would call a QGP. And this is why we would let it emit, and it just gives you something of double the temperature. So this would be no QGP. And this is then, so that is, it is a large factor in that case.
But if I go to higher PT photons, they come from an earlier time, I guess?
On
or,
average, yes.
On average. So I'm sort of pushing myself to the right of that curve. So I guess if I measure 400, I know that I'm hot because the blue shift is going away. But like, I haven't really got a feel for how, yeah, okay, when it's 200, it gets me to 300, but then when it's at 350, it hasn't shifted it. So like how much variation I can have in the blue shift to move that away.
Yeah, this goes also in the same direction that, for example, at RIG, we have been fitting the spectra with different fit ranges, right? We have a low PT fit, intermediate PT fit, high PT fit. Yeah, I would have to recalculate maybe this one. Yeah, okay, but they are here, right? So this exercise is a little bit in here, in a sense, because here we do have the fit from 2 to 4 instead of from 0.5 to 1, but then you're biased in time. And then indeed you would think that the blue shift contribution to this one would already be lower than to this one. Yeah.
So what you've shown us, if I did 2 to 4 and got this value of 360, I have shown it's above TPC, right? Because you say, okay, the blue shift effectively gone.
Yes.
Sort of tells me if I can do that. I don't know. Let's see. If there is a way that I should see it vary and then sort of asymptote somewhere, ideally. Maybe.
Yes, but then in some way or form we still have to invoke the model in quite a more, or in a bigger way than for dileptons.
You need to quote the model to say that it's not.
Yeah. So if we let the model, yeah, if we indeed use the model, I think we can extract upper limits for how much the blue shift can actually do, and then still make quite a strong statement. But if we want to, because in my opinion, I think if we with thermal dileptons would measure a temperature 5 sigma above whatever Lattice is predicting, we could write a Nature paper on this, and it would be best, I think, if there's no model
Great.
involved in that. I think that would be good, and that's basically the main point I want to make. I'm also not saying that Alice or any other one we should completely abandon photon analysis, because indeed they still have information, right? Okay. Then the somewhat complicated plot, which I think is a very cool, and I would say it's the money plot. We hang it outside our office on the door. So to introduce this one, so using the model, what do we have? We have the QGP temperature as function of time, right? You should already see this in the bands in the back. It's now a linear scale. And you see the QGP temperature as function of centrality evolving over time. We also have dilepton production in the model. And whenever a dilepton is produced, we can ask it when it is produced, okay? And we can feed that into a file. We can have a dilepton and it can say, I was emitted at a Fermi over C tau of 2, okay? Etc. We also can perform the measurement as if it is a data in the model. So we can extract the effective temperatures that are also shown here, right? By using that fit of the invariant mass. Now we can put all those 3 things all together in one plot. So we just have the QGP, evolution. And then for every analysis cut, so we can make cuts in, like we do here, we have different selection criteria for our dileptons that I was so far always hinting they are produced on average at different times. We can ask that, we can create a distribution, calculate the mean, and the sigma, or the quartiles, more specifically, and put them on this plot, okay? So on one hand, we have the bands, it's just a model. Then we can do our analysis, our dilepton analysis, which has selection criteria. For example, a very high or very low invariant mass selection. These will come with their own distribution of when they were emitted. So this we can put here. So we have an effective temperature at the median. So this is the median and this is the average. So every dilepton analysis has a mean and an average, and then of course you have your quartiles. So you can see that it's a bit of a skewed distribution, that if this is the mean and this is the median, so the median is of course the most probable value. So distribution would peak here and then have a long tail to the right. So this is the emission distribution of a dilepton analysis with a specific invariant mass cut, right? And you, from that sample or that analysis, you can also extract an average temperature, okay? And this temperature for this point happens to be 250 MeV, okay? Now what is cool is that since we have the distribution of their emission times and the temperature, we can put them on this plot. And we also have the information of the plasma as function of time. And why I'm so happy about this plot, and it's a bit of a confusing plot, but what I'm happy about is that the filled points, so the red points are the dilepton analysis in central, the orange are in 30 to 40%, and the blue are in peripheral. The filled points are on the lines of the model, okay? And what this means is that we can perform these dilepton measurements. We know from the model when they were emitted. We have the temperature. Then we can ask the model, what was your temperature at the time when I also thought you were emitted? And it's the same temperature. So now it's sort of the circle is round. And this will mean that if we do the measurement using the model with certain analysis cuts, then we also know by informing or using the model, we know when they were emitted. And we can map the temperatures to different stages in the model, okay? And it makes sense. So it could, before we made this plot, we thought maybe these points are completely off because we started to do this and we were like, let's plot the means, but all the means were completely off. And we thought, okay, what would more drive this sort of distribution of the emission? Maybe it's the median, and the median happens to be on top. So this but okay, that's also why we put these arrow bars to show the width of these emission distributions. But you see that also for lower and lower times, when the temperature is hotter, also these distributions of the emission times gets much narrower, and the temperature also go up. And this shows you that this is then also completely undoable with photons because you don't have the invariant mass, and using dileptons, so they can accurately measure the QGP temperature all throughout its evolution, and we can use the selection on PT and the mass intervals to really scan through this time. I think this is really cool, and that is what we sort of found out in this paper, and you can read more about it also in the paper. And part of my grant is to do something with phenomenology, but also to do this actually in Alice, right? So to do the actual dilepton measurement. And that brings me also to the end. So I thank you.
So on your money plot, two questions. One is, why for the most central do you not go to earlier times like you do for the peripheral? And it looks like the error bars are, maybe I'm wrong, or the uncertainties are better, let's say, for the peripheral. Am I wrong?
Yeah, so if you look at where
Solid points.
first, let's see, first your first question. So where you see where the
Right,
band
and just
starts
look
to
at
be
the
colored.
solid red, the closest, the shortest time versus solid blue.
Yeah, so the model will always start at the same time for every centrality. So the time at when this band become colored is the same everywhere. What we then do is
Oh, the centroid moves then, you're saying.
yeah, it's a bit misleading, and then maybe I should have included a plot in the backup, but these are just the quartiles of the emission distribution. So we can do our analysis cuts. So we can, for example, say we would like to do the analysis with the dilepton with a certain PT and invariant mass cut. That will give us a whole distribution from 0 to 10 of when they were emitted. And this distribution, which looks a little bit like a Personian or so, will have a median and a mean. And the mean is always on the right because there's a long tail. And here we just put the error bars are just the first and the third quartile. And it just happens to be that these ones are more narrow. So it's not that these are only emitted later, but it's just that this distribution is maybe a little bit more narrow. It's not that they are not emitted early. Yeah.
The second question doesn't apply. That's fine, thank you.
I think a quick question on slide 9. Yes, I just didn't have enough time to, I think, to read the plot. Can you explain the difference between the solid and, oh, I see, sorry. It's
Yeah,
higher
exactly.
in
I didn't
PT
explain
and
too
then-
much. Yeah,
okay.
exactly.
I just saw quickly those much larger numbers for the effective temperature, and I wasn't sure how you were getting such a big difference, but I guess it's just they're fit over a different PT range, and the PT is, okay.
Yeah, exactly.
Thanks.
So the solid column is just, this is the fit interval, and the best one is this one, and they are listed here separately.
Okay, yeah.
So I mean, on your phase diagram, you have much larger errors than those.
Yeah, so I must admit that for my grant interview, plotting 1 sigma. So I made this 2 sigma, which is why I now also say it's a 2 sigma uncertainty, because if it's 1 sigma, it already looks quite convincingly higher than. Then I would have to convince them that we're not satisfied with it. Right? So that's why I made the error about 2 sigma and didn't go into too much detail for the committee. But yeah, this is indeed a 2 sigma. That's also exactly what I write here. So it's this one is this 2 sigma
Yeah,
interval.
Okay.
I would like to have it 5 sigma. Yeah. It's a simple message. Yeah.
On your money plot, you said, in Trajectum that it seems that these median times fall right on these kind of Trajectum curves. You said you expected at first it to be the average. So now that you've thought about it more, do you think it should always be the median, or you think this could maybe just be it happens to be so in Trajectum, and maybe in other models the mean might be a better indicator?
Yeah, I don't think it's a bit of a philosophy. Maybe there's just a mathematical answer, but if you have an emission spectra that has a certain shape, it's not just the median, right? It's not just the highest probability that will completely dominate your temperature. It must be the whole distribution.
Mm-hmm.
So I would expect it to sort of lie in the middle. But it's a bit of the philosophical question. If you have a whole distribution, will you represent that distribution? You want to represent a distribution by a number.
Yeah.
And is then the median or the mean a more representative number of your whole distribution, right? Yeah, so I think that is just like a statistics philosophical question. I thought about this. And of course, in the beginning, indeed, we just plotted the mean. And then we thought, okay, means are more easily skewed by tails, right? That is also why if you would plot or say what is the average wealth of a person, for example, it skews very high because this distribution goes way too far positive and not negative, right?
Yeah.
Yeah, so I think these are just 2 numbers that we happen to be able to quote. I think that's the best answer. I think one should always take into account the whole distribution. But we're sort of happy that for most of them, also, for example, for this point, the line sort of goes in between the median and the mean. but it is at least always at a point where if you look at the distribution, the amount of emissions there is very high. And then that corresponds well to the temperature, so.
Yeah, I guess that's my question. Is it like a happy accident that the median gets it in Trajectum? Or is it really like if you tested a bunch of different models, you would expect the median to be kind of the best we can
That's
do?
a very good question. I don't know. I don't know if that's really a Trajectum feature or.
Assuming your
or a
temperature
happy
is falling with a similar shape, I guess it must be more true that the median, right? There's a skewing of the temperature to the left of that distribution of the
Yeah,
masses
because
will be
median-
hotter.
Yeah, exactly,
It's sort of
because
an integral of those somehow, right? So as long as temperature drops steeply at the beginning and then plateaus, I guess your median.
because medians are less sensitive to outliers, where also the QCP spends less time, then the median should be more representative. Yeah. Yes.
So long back when we were looking at the Boltzmann transport model, to do the same thing basically. And the issue always used to be like eta over S was the input, and it changes everything. Does it also take eta over S as an input, or yeah?
Yeah, so what we have actually done, and that is also why there are many different lines here. So the eta over S, first of all, is constrained by Bayesian analysis. I don't know if you're familiar with that.
Somewhat.
Yeah, somewhat, yeah. So you have the experimental data, and there's this whole fit procedure to get the posteriors of the model parameters. And this will then, of course, form a distribution. And the central values of what we show here is what we picked from the most probable values from all those posterior that we get out of those Bayesian fits. And then for the systematic uncertainties that are even in all these spectra, like here, so also I think why this is sort of a cool theory paper, is that we run the analysis really many times by taking different points of of those posteriors. So we walk around this n-dimensional plane of all these different model points, and this is what generates a systematic uncertainty even in a theory paper. And the eta over S, also the bulk viscosity, it's all varied according to the posterior of the Bayesian analysis. Yeah.
So that's very cool to see. Now another thing was, does this also work for like high multiplicity PP or something? Because that's also they discuss like maybe the forming a medium and all those things. So will this also work for that? Or?
Yeah, so the difficulty is that for the initial state, the proton is not so well known, so it's difficult to generate that. And Bayesian analysis are very hard to get working on PP collisions because the measurements are all over the place and it's hard to constrain. But the people so there are also now a few oxygen papers out of Trajectum, so we're definitely working towards smaller systems. And there has been one time an effort to try to do PLED collisions in Trajectum with Bayesian analysis, also turned out to be difficult. But certainly, yeah. I mean, in general, yes, there are many models like EPOLs or so that have some core production, where this would be interesting. Yeah, I would hope so that we can get there. Yeah.
Okay, thanks. Let's thank Mike for this nice presentation. So for that plot, what if you just put the shape